Okay, well, good morning, everybody. We might as well get started. So in today's session, well, in the morning, we're going to be looking primarily at the sort of main subject of the course, which is micro-injection moulding. The structure of this talk is basically just an introduction to conventional injection moulding, just to give you the sort of basics of how injection moulding works, why it exists, what the benefits are and advantages are of this particular process. And then what we'll do is we'll introduce how micro-injection moulding machines differ slightly from these conventional pieces of equipment in order to kind of solve potential problems when using conventional injection moulding for micromoulding type geometries. We'll then look at some applications of micromoulding techniques, so areas where we're using micro-injection moulding capabilities to make very high accuracy structured surfaces, achieve very, very fine tolerances with different parts, and showing how we can use those in a range of markets for functional devices. We're then going to look at what we're doing in terms of the materials in the micro-injection moulding process. So what's going on in terms of the way we're handling these materials and how we're structuring the internal morphology of materials to give us certain physical properties. And finally, I'll finish up by highlighting how we're addressing some of the questions raised by this area here with some of the research activities that we're doing in the micro-injection moulding laboratories, which also links closely with what you'll do later in the hands-on workshops. So basically, injection moulding technology, the majority of polymer parts where you've got a fairly complex three-dimensional shape in thermoplastics will use injection moulding as a manufacturing process to manufacture these parts. It's a net shape forming process, so basically it means you can output an object which is pretty much the final shape that you wanted at the start of the manufacturing process. There's no real finishing work required. And basically you can achieve very, very good quality, very, very high accuracy, and you can also make large volumes of parts using this kind of technique, which is why it's so common throughout the world for making mass-produced goods. In order to form these parts, we're using fairly high forces and pressures, so an injection moulding piece of equipment tends to be a rather large machine to cope with these very, very high pressures and forces. It needs to be able to handle high stress in the frame of the machine. And as I said before, it's basically, its reason for existing is to make high volumes of parts at a comparatively low cost using thermoplastics. Historically, these were always hydraulic machines in order to deal with these very high forces that are required for doing this manufacturing process. But recently, since, say, the mid-1990s, there's been a big shift towards servo-electric driven machines because they offer a much higher precision, almost like CNC, like precision and control. And they also use less energy than the hydraulic machines as well for the majority of components. So even though they cost a little bit more, there seems to be a general trend moving that way, particularly with the increased cost of energy. So we make a huge variety of different kind of components using the injection moulding technique. Some of the largest injection mould tools in the world are used for things like car panels, bumpers, sometimes they're sort of like crash impact zones, that kind of thing. But then there's a whole spectrum of device sizes in between, from computers, TV surrounds, all sort of forms of plastic housings and that kind of thing, all the way down to the origins of micro-injection moulding for things like watch gears, so small plastic watch gears for companies like Swatch, that kind of thing. So you can see that all of these have more complexity than the things that Dr. Kelly showed yesterday in the extrusion lecture. We're no longer looking at constant 2D profiles. We have these kind of these 3D geometries that we can only form using a mold tool and using an injection moulding process. So some of the features of the process. The cost profile is quite interesting. People always say, additive manufacturing, 3D printing is becoming ever more popular. So in the future, perhaps everybody will use additive manufacturing techniques to make components. And whilst that's true to a certain extent for customized components, things where you want a specific shape for maybe just a few samples, or maybe up to 1,000 samples, it still remains competitive. And that's mainly because injection moulding processes actually have quite a high initial equipment cost. So to make one part, you have to buy a moulding machine, which you can use for a range of components. But then you also have to invest on an injection mold tool. So basically the cavity that forms the shape of the part you want to manufacture. And due to the engineering required for those mould tools, the costs tend to be quite high, so ranging from a few tens of thousands of pounds to millions of pounds in some cases for things like the automotive example that I showed earlier. So there's normally fairly high capital equipment cost and the tooling cost. You've also got to have additional capabilities like material handling capabilities, drying capabilities, that kind of thing in your factory. But the main thing here is the materials we're using are actually comparatively cheap. Adrian discussed the benefits of thermoplastics yesterday in the fact that they're easily formable, they have good mechanical properties, but overall the cost is pretty good. And we can make them extremely quickly as well. So even for the large parts, we generally have less than a minute cycle time for one of these machines to make each component. For the smaller parts, that can come down to just a few seconds in many cases. You don't really have to look after the process. It's got a low labour cost because basically the machine will run in a fully automatic mode. You can integrate that with an automated system. And so what these all mean that even though you've got this initial high investment cost, the marginal cost, so the cost to make one more component, is actually pretty low. So basically, if you're making really high volumes of something, you've got quite a high initial profile, but then the cost profile flattens out significantly, and you can start to make some significant profits. And so that's why, that's kind of why injection moulding is best used for very high volume manufacture. So let's have a quick look at how the process works. This is an animation supplied by Engel, who are a company who make injection moulding machines. They do have a nice funky soundtrack to go with it, but it's going to get in the way of my talking. So basically, the machine is split into two individual areas. Basically, you've got the material, so the plastic melt preparation side, which is this side here, which is going to do the melting of the material. And then here we've got the mould side. So this is clamping the mould together, where our mould sits in there and also has things like the ejector pins that pop the part out of the mould. So if we look first of all at the injection side of this, this is very similar to the extrusion process that Dr. Kelly discussed yesterday. So inside this heated barrel here, we have basically an extruder screw that's operating the exact same way as Adrian discussed yesterday. So we have basically a feed zone, a compression zone in order to basically convey and then melt the material. We also have a chilled area here as well to stop any problems with pellets spilling around the screw and not feeding forward, as was discussed yesterday. The main difference is, at the end of this screw, we have a small valve. We basically have a check ring, because the screw is now no longer fixed. The screw actually moves backwards and forwards, which gives us our injection stroke to force material into the cavity. So basically, the screw only turns as it moves backwards in order to convey material through into this melt reservoir here. And then what happens is the screw moves forward and this valve closes, and that's able to force the material into the cavity. So it's a little bit more complex than the standard extrusion process alone. But basically, it's this injection action, this forcing forward as a ram of the screw that actually forces the material through our nozzle and into our cavity form here, which makes the shape of our component. Okay? So as you can see here, the actual screw geometry is pretty similar to the conventional injection moulding process. So this side of the machine is all at the melt temperature of the material, which can be anywhere between 200 degrees and 450 degrees. The mould side is much lower than that, so typically mould temperatures range between about 40 degrees and maybe up to 200 for some of the high temperature polymers. So this is it's cooling in this region here and solidifying, which forms our final part. So that's the basic overview of how the process works. So if we look at those individual stages in the process, we've got two basic steps. So we've got the melt generation and the production by the rotating screw. We've then got this forward motion of the screw that actually forces the material into the cavity to form the shape of our part. And so what we can do is we can break up this filling phase or this cavity filling phase into a number of key parts of the injection moulding cycle. So basically, the first part of the process is the filling stage. So we're injecting the melt into the mould cavity. That's the first movement of the screw. But then what happens is, as it's doing that, the screw is moving at a constant velocity. That's the setting on the machine. We tell the screw how fast to move, because that's going to influence the shear rates that we're having and basically the speed it takes to fill the cavity. But if we stayed in that constant velocity control and we filled the mould cavity, we would get a sudden increase in pressure because the material has nowhere to flow anymore, and so there'll be a big spike in pressure, and that can in some cases cause damage to the tool. So what we actually do is we part fill the cavity to about 99% full, And then we switch over the control of our screw from a velocity-controlled regime to a pressure-controlled regime, okay? So now we can no longer see these pressure spikes. We can impose a pressure limit on the filling phase of the process. And so what we do is we then sustain that pressure for a given period of time. So basically, what we do is we fill the cavity under a pressure control and we hold that pressure on there for quite a few seconds in many cases. And what that is doing is that's countering the fact that as the material is cooling and solidifying, its volume changes. Basically, it becomes more dense. And so what it's effectively doing is shrinking inside the mould cavity. So by sustaining that pressure after the part is filled, we're able to squeeze in a little bit more material to fill that volume that's left by the part actually solidifying, okay? So imagine it's cooling from the contact with the mould surface, so you've effectively got a kind of sandwich structure of a frozen layer on the outside of the part and a soft molten core. So by continuing to keep that core under pressure, we can take into account some of the shrinkage behaviour in the material. And what I can do is you can actually see, I'll pass around a very simple injection moulded part. It's a test specimen here, but you can see this is the sprue, so the nozzle tip will end here. This is the sprue that takes it into the mould. The mould splits down the split plane here. And you might be able to see things like little circles on the back of the part that basically indicate the location of the ejector pins. So we have an array of pins that actually pushes the part out of the mould once the cycle is complete. So it's an effective way of removing it. But if you look on the back of the part here, where we have this rib junction, and another thicker section here, you will actually see a slight sort of indented area in the back of the tool, which is caused by this shrinkage process, okay? So it's quite a nice visual indicator of what's going on. So they're the two main parts of the process. What's going to happen, though, is after a certain amount of time, one of the smaller sections on the part is the gate, so the bit where the polymer enters the cavity, and that's going to freeze fairly early in the process. And once that's frozen, it doesn't really matter what you're applying in terms of pressure, because if you can't continue to fill the part, then you're not really doing anything with your hole pressure. So we stop that hole pressure there, and then we just have an additional time period for cooling. So basically, we're no longer applying pressure to the cavity, but we've got to wait for the part to cool sufficiently that we can eject it without permanently deforming it, okay? So we have to wait until it's we're well below the heat deflection temperature. And once that's done, basically then we're just concentrating on preparing the next shot, so the screw will go back again. We decompress it, so we take a little bit of pressure off that screw as it screws back to avoid material sort of leaking out of the nozzle into the next shot. And then we open the mould and remove the part. But they're the basic, the basic parts of the process. So I mentioned the screw before. The screw is very similar in design to the ones that Adrian discussed yesterday. And likewise, we can also choose different screws depending on what materials we're using. So generally, this compression zone here can have different compression ratios for different materials. But the important bit is this check ring that opens and closes at the end. So basically, we have this ring of material around this end of the screw. So as soon as we start to push the screw forward to act as a ram, then basically the friction on this ring here, it means it's forced back to seal against this surface here. And once that seal occurs, there's no way the material can actually be forced back over the screw. So it makes sure you get a really good positive displacement of injection into the cavity. The problem is for micro-injection moulding is if you're trying to inject with really, really high precision, the movement of this ring backwards gives you a bit of a lack of control of the volume of material just in this area here. And that volume in many cases can be the size of a considerable number of parts that you're trying to manufacture in micro-injection moulding. So it kind of introduces a slight unknown in terms of your dosing capability and your injection capability. If we look at a typical pressure profile going through the cavity, this is what I was saying before. So we have this initial fill level. So basically the gradient of the curve in this fill region is an artifact of the geometry of the cavity. We can actually see different increases in the filling pressure here, and we can relate that to different sections in the cavity. So basically, if you have a very thick section, you're going to have a fairly shallow pressure gradient here to fill that. If you have a fairly thin wall component or a narrow section, then you're going to need quite a high pressure gradient to get the flow of material to go down there. So this here is the important bit. This is the bit I was talking about before where we switch over. So about 99% filled. We switch over from the velocity control to the pressure control, and then we sustain that pressure in the cavity to take into account the shrinkage. And once that gate is frozen, we're not doing any more, then basically we're in the cooling stage and the pressure will start to drop off to zero. And then we can eject the part. So this shrinkage is an issue, and basically what we want to do is we want to minimize the effect of shrinkage on our components. And so that's why the majority of injection molded parts that you see will tend to have some fairly thin-walled rib-like structures to give them the sort of mechanical strength that they need. We want to avoid thick sections because thick sections are going to cause problems because they're difficult to pack during this hold stage of the process. So I'll pass round one here. You've got a nice example of a kind of rib structure here to build strength. This is also interesting as well, though, because it's a water-assisted injection moulding component where water is actually also being used to hollow out this main thick section here. And this is actually the clutch pedal from a BMW i8. So it's a carbon fibre filled plastic component that's made using these kinds of processes. But the important thing here is we need to avoid these thick wall sections because they're going to cause problems with shrinkage. And we also want to avoid long flow paths because that's going to require higher injection pressures to actually fill the cavity. So here's an example of how wall thickness problems can manifest themselves. Basically, where you have thick sections here, we can actually start to see sink marks, as you'll see on the first component that's coming round. So basically, as the part cools, we've got this kind of reservoir melt in the central section of this rib. And basically, if we're unable to pack that, because once again, I say if this plaque area here freezes first, then the material will be kind of drawn in by that material that's sinking, that's shrinking to give us this kind of defect here, which is very, very common on the majority of injection moulded parts. Even worse is what can happen if it adheres to the mould surface here. You can get internal voids occurring as well. So the material shrinks, which is causing this internal voids, which you can't actually see with the naked eye, but you've got a weakness inside your part. So it can cause real problems. So what we would tend to do here is you can actually apply a rib on the mould surface, which actually keeps the thickness very similar. So basically the shrinkage will be taken account of all at the same time. So we can core out these thick sections. Another very effective way of keeping the strength of a component but keeping the wall thickness uniform is just to use ribs as well. So in the example we have here, basically by using arrays of rib sections here, we're using the second moment advantage to increase the stiffness of the component, but we're using less material and we're using thinner sections, so it's going to have benefits that we don't have any shrinkage. But also another one is we're keeping the cycle time as low as possible as well, because most of the time spent in the tool is waiting for it to cool. If we have these thin wall sections, then basically that's going to cool much quicker, reduce our cycle time, which means we can make more components per day, which is a good idea for moulding. Another thing we have to consider is getting the part out of the mould once it's been made. Because this shrinkage is occurring, if you imagine you've got like a cylindrical boss in the tool, it can shrink onto that cylinder and it can be sometimes quite difficult to release it. So what we tend to do in our mould designs is we'll apply at least 1 degree, sometimes more, of draft to each of these walls in our mould. So basically, if we have an undrafted component like this, we risk having trouble ejecting the part. Sometimes the force is required for the ejector pins to push the part out of the tool, so we maybe be pushing on this edge here, can be enough to damage the part. We can cause cracking behaviour during ejection, which is a problem. However, if we put a nice draft angle on something like this, then obviously as we push on the top here, it easily gives way and it comes out of the mould okay. So this is something we have to consider. And this is all done in the mould design sort of stage of the process, basically. What we will do is we'll look at the material we're using. We'll be able to, from the manufacturer's data sheets, we can estimate what the shrinkage is going to be for that particular material. And then we effectively just make the tool bigger to compensate for the shrinkage. If we know the material is going to shrink by, say, 2%, we can make the whole tool 2% larger in each dimension, and then we'll get a part that comes out at the required dimension. So during that tool design process, we can't really change it. We've designed the component at this stage to make sure it's suitable for the injection moulding process, but then we still have to think about things like where we inject the material from on that part design. So gate location can be quite challenging to do, because what we want to do is make sure we get a nice kind of uniform pressure distribution throughout the part, but we want to avoid key problems like things like weld lines. So basically, wherever we get two flow fronts coming together, we're going to get basically the coldest part of the material coming into the cavity is actually at this flow front here. So that cold material is going to not knit as well when it impinges on itself, basically. So we have a problem that wherever we're flowing around bosses to make holes in our part, we've got these two flow fronts come together and we form these weld lines or knit lines that you can clearly see on many components. And they're a source of weakness. Basically, the molecular chains, the molecules in that region aren't completely sort of diffusing with each other. Basically, we have a boundary there which can cause stress concentrations and it can guide fractures. So in many cases, we can't avoid these because if we have a hole in our part, there's no injection location on this part that we can choose that won't cause a weld line. But what we can do is maybe look at the FE modelling and make sure that these weld lines don't fall on really highly stressed parts or areas of the product, okay? We also have to look at the size of the gate and the gate location to avoid problems like this, which is a jetting behaviour. So rather than a nice uniform filling pattern that we see on the top part here, particularly for fibre filled materials, we can see this kind of snaking behaviour. So the material will snake into the cavity. So effectively now you've got a whole mass of weld lines all inside your part. So you have real problems with surface quality because you'll be able to see these kind of flow marks on the surface of your product. And also the mechanical performance will never be as good because we're not getting the benefits of a nice shearing flow, which is causing orientation of your molecules and your alignment. We've got this much more random distribution with internal weaknesses as well. So these are things we have to consider. So as I say, on most components, you can see where these weld lines occur, and you can see that they'll exhibit themselves on the surface of the part, and they'll also cause stress concentrations as well. So if you don't control your weld lines adequately, you're creating local failure regions in your component. So that's a sort of a brief overview of the conventional injection molding process. The machine we're going to be using today is the Wittmann-Bettenfeld MicroPower 15, which has made a few modifications to sort of standard conventional injection molding to overcome some of these problems. So first of all, with making these smaller components, what we want to do is reduce the amount of material we're having to use to make each shot. So in the first part that came around there, we've got quite a long sprue on there, which is quite a high volume of material. So what we've done with, what Wittmann-Bettenfeld have done with their machine design is we still have a fixed screw here, but basically we've done away with the checkering. So we no longer have that checkering there, which is causing this problem with this unknown amount of material that could be conveyed in that checkering. So this screw still moves backwards and forwards to dispense material, but by not having this checkering in here, we're able to deposit slightly more accurately. But then what we do for the injection phase of the process, I mean, because this screw doesn't have a checkering on there, we can't use really, really high pressures because obviously the polymer will just be forced back over the screw because we don't have this valve type system. So what we do is we use the movement of this screw forward at a fairly low pressure to actually just convey material into this injection piston here. And this injection piston is then moving forwards, I'll just play that again, and taking material into the cavity at very, very high speed, but also in a very, very well-controlled manner. Because the problem is, in many cases, we're filling this cavity in milliseconds, like a single millisecond in some cases. So this piston is actually having to bring material in here. It's having to switch over incredibly quickly when that part is almost full, and then switch to this hold pressure. And if you actually look at the requirements for the controller of this injection unit, they're really, really demanding. But basically, the benefits are good. Because basically all our material is going into the cavity, so we don't leave any sort of melt left in the screw, unlike conventional injection molding where we have this melt cushion material, which is going to then go into the next shot basically. With this one, the entire shot is distributed into the cavity. We don't have any sprue material, so we're minimizing the amount of material that we need to use. And we've got a nice separation between the cold mold and the hot material preparation area as well. In a conventional injection molding machine, you've got this constant contact between the hot nozzle and the cold mold, so you've got a bit of a pressure gradient in there. So the first shot of your next cycle, or the first part of that shot, will actually be a little bit cooler than the rest of the material behind it, and that can cause problems with micro-injection molding. And the last thing is, in micromolding, we're not really waiting for things to cool. These things cool in fractions of a second. So a huge part of the cycle time in conventional injection molding is kind of irrelevant for micromolding. So we can actually increase our production outputs by having two tools mounted on the same machine, which allows us to remove the part from one tool and inspect it or assemble it as we're molding the next part. So we effectively get a reduction of the cycle time of about half by having this two-tool system in there. Okay, so once we have these technologies, we can use them for a range of application areas. So I've separated them into a few different ones here. The first one is sort of engineering components. So these are components used for their sort of mechanical property behavior. In this case, it's kind of actually a sort of thermal behavior because we're using a highly nanotube filled material. But these we're looking at sort of structures and strength and also very accurate sort of dimensional control. So a nice example here is a part which is a peak bobbin. which requires tolerances of just under sort of 10 microns for the gaps between each of these fins. And what this acts is a bobbin for creating an inductive sensor. So basically a copper wire is wound around this bobbin. So we have to make sure we have no stress concentrators, split lines or edges on here that could break that copper wire. But that's a nice example, and it's an inductive sensor used for measuring the coating thickness of electroplating, basically. But other examples, we've got mechanical components. I mentioned sort of things like watch gears earlier in polymers. And we can also use different materials like metal and ceramic powders. So this is from a collaborator over at Karlsruhe Institute of Technology, where they're working with ceramic filled powders. We've also done some of this work at Bradford as well. So effectively, we're using injection moulding but we fill the tool with ceramic powder and a polymer binder. We can then put them in a furnace. We remove the polymer binder to create like a ceramic scaffold, and then we can sinter that component to make a final almost, well, sort of 98% solid ceramic part as well. So it gives us the capability to use different materials for different applications. Another big area is optics. We can work closely with sort of people who produce very high quality tools using diamond machining techniques, so they can directly machine optical surfaces. Well, when we get those parts, we can then replicate those optical surfaces in a range of polymers using a sort of micro-injection molding process. We have these very, very high pressures with our injection piston, which allows us to get very good replication quality of these kind of structural elements. So we do things like Fresnel lens molding, we can do diffraction gratings. And this is a light harvesting device. There's an anti-reflective light harvesting device for photovoltaic applications. So basically we can increase the efficiency of solar cells rather than having sun tracking systems by having some clever sort of polymer collectors mounted to the active element. So we've done a range of work in this area. Another one is dentistry, surprisingly. We've done a fair bit of work with different dental applications. This is one of those, which is the core for root canal treatment that goes down the nerve of your tooth if you were unlucky enough to have had a root canal treatment. And basically this involved lots of development work on getting the material right. So it's a two-component nylon, heavily filled with a zirconia material. So we had to look at how the material flowed, how we could ensure that the process was going to be a success. And then this is taken away, and a coating is applied to this core. So when it goes into a root cavity, it actually absorbs a little bit of moisture in the area, swells slightly, and avoids the chance of reinfection. So this was something developed at the university, which is now out there in industry and is being used to the tune of probably about 1 million components so far. So it's been quite a good success. It also offers significant benefits over the current technology too. Another example, I used to show the video for this, but I have to be a bit careful because people start to feel a bit faint and ill. But we do medical devices too. So the scale of this I'll show you in the labs later. I mean, the capsule itself is about this long, so it's not the kind of true micromoulding component, but in here we have some detail. We've got an internal surface finish and a profile, which is designed to handle very, very thin materials from the human eye. So basically, there's a certain type of cataract that affects the back of your lens in your eye. And for that to be treated, the surgeon has to basically go into the eyeball itself, and he scrapes that material away that's gone opaque and cloudy. But he needs to replace that with something, so he'll take the same material from an eye that's been donated by a cadaver, but this material is only about 50 microns thick, so it's like a tiny circle of cling film, which he needs to then get back into the eye again. So we worked with the company to develop this technology, which uses this capsule here. And basically what happens is we place this tiny thin sort of endothelium in this part of the component. We use forceps coming through the part to draw that into this capsule here. And the detail inside this capsule automatically rolls this tiny thin bit of material up to make it more compact. But of course it has to do that without tearing or shearing the component in any way. Then this is taken, it goes into the eyeball itself, and another forceps is used to remove the component in the eye, and it automatically unfolds. You can put a bubble of air behind that, and that will graft to the site and give a really, really good outcome compared to the alternative, which is full cornea replacement surgery, where you basically use a hole punch to punch out the eye from a donor and then put it straight into the patient here. So it's much less intrusive and gives much better outcomes over time. But obviously, it poses real manufacturing issues because we have to make sure there's no contaminants in here. And also, we have to avoid any kind of flash or bits of material that might be hanging off the edge of this component, because if they break away in the eye, they'll be there for the rest of the patient's life. So there's some significant challenges to be looked at. We've also looked at things like reel-to-reel processes. So this is an interesting variant of the micromoulding process where we pass a filament through the mould and we can mould any kind of structures onto that filament. So in this case, these are kind of almost spherical beads. So we pass the filament through, we're moulding 4 at a time, and then we can create these kinds of objects as well. So more kind of chain objects inside the process. Once again, it requires quite a lot of care in doing this. So we needed to measure the tension we're putting on the filament, measure the Poisson's ratio, so we can measure the actual diameter of the filament, and that allows us to cut our mould tool so it's a perfect fit, and we don't have any problems with flashing down the string from bead to bead. We do lots of work in looking at functionalized surfaces as well. So we might be looking at larger parts, but using micromoulding techniques to replicate micro and nano features on these kinds of surfaces. So we can have structures down from a few hundred nanometers in this case to a few microns for a whole range of applications. We've looked at antimicrobial, we've looked at cell culturing applications, and we're also looking at things like bearing applications as well, tribological applications such as friction reduction and also things like acoustic behavior of materials as well, so anti-squeak properties and that kind of thing. Another example is we can also incorporate these micro and nanoscale details for anti-counterfeit activities as well. So this is a project working on at the moment. This was some early work looking at QR code. So here we have a laser machine's QR code pattern, but then within a single pixel of this, we've repeated the pattern again using focused ion beam milling in the mold tool. So the features here, this is about 2 millimeters in terms of the side length, whereas down here, each one of these pixels is around about just over a micron in side length, and the depth of that is about 500 nanometers. So we've got a kind of microscale and nanoscale pattern to protect parts. And once again, it's got a quite nice profile for anti-counterfeiting, because although the tool insert is quite expensive initially, after that there's no marginal cost. So you're not paying for dies or RFID tags or that kind of thing down the line. And it's also a nice process quality indicator as well, because if you had a low quality counterfeiting process, you wouldn't be able to replicate this feature anyway. So basically you'll be able to tell that from the parts if someone did manage to copy your mold insert. So with all these applications, what are we actually trying to achieve? We've got all these different demands from our customers, and basically their wishes could be, obviously one of the most important ones is form, ultra precision accuracy with the dimensions that we've been given by the customer. But then with that come all sorts of other requests as well. It's got to obviously have the right mechanical properties because it can't break in use. We might be working with optical materials, in which case transparency and birefringence become important. And there's a whole range of others as well. So electrical, thermal, for the pharmaceutical applications, it could be API solubility or sort of antimicrobial behavior. We might want to have some kind of behavior there as well. So we've got all these demands on us for our different materials. And so it sometimes becomes quite difficult to understand or be confident that we've got the optimum process conditions to get the best out of these materials. So if we actually look at the problem that we're faced with, we've got our input materials here, which all have different properties. They flow in different ways, they will crystallize in different ways. We might have amorphous materials which don't crystallize at all. They get different surface energy effects, different thermal behavior. And so what we do here in this lab is we make sure that we can characterize each phase of the manufacturing process. So we understand from a material starting point what we're doing to them all the way through this manufacturing process. So then we can start to be able to predict what we would expect the final outcomes to be in terms of the performance of our components. And that's basically the structure for this whole workshop. I mean, we've already looked at the extrusion. Today we're talking about injection molding. What we're going to do is look at how important these things are. So this afternoon we'll talk about the rheology of the materials, so the flow behavior of these materials and how that's relevant for this process. Tomorrow morning we'll talk about morphology development, so how they crystallize and how those results in the final properties. And then on Friday we'll actually look at measuring those properties and relating them to what we've learned here. But what I want to focus on in this talk is basically how we understand what we're doing to the materials in the microinjection molding process. So how can we take measurements to be able to characterize the environment that we're exposing these materials to, so that understanding how these materials behave, we can start to be able to predict these final properties. And this is basically our kind of unique our sort of unique selling point in this department, this research department at Bradford. We don't do tooling, we do some process development, but we don't make manufacturing hardware. But what we do is generate understanding of how these very, very complicated materials, these long chain molecules, behave in given environments, so we can start to predict what the outcomes are going to be for our micromolded components. So I'm going to look at some research areas that deal with this kind of measurement capability. How do we interrogate the process to understand what we're doing? How can we use that to troubleshoot processes and make fundamentally better components? So the first area is the sort of sensor technologies. So these are some of the systems we're using in the labs and some things that you will use later on this morning in order to understand what's happening in this process. So this is our micro-injection molding machine, and just to give an example of the kind of the extra sort of measurement capabilities we install on this machine, I've got some examples in the slides here. So one of the first things we did when we got this machine was we wanted to understand the injection kinetics of the machine. So we actually installed a laser displacement sensor on the rear of the injection piston inside the injection unit. So here we've got a laser triangulation sensor. We've got a target mounted on the back of our injection piston. So the piston is actually attached to this piece of metal here. And that gives us a very fast, about sort of 3,000 measurements per second way of measuring the position and the velocity of this injection piston with time. Now, you may wonder why we have to do that, because we've actually got an encoder on the main servo drive that drives that injection piston. But the problem is, the encoder is mounted sort of down here, some on the main drive unit, but then we've got this belt system that's actually transferring that motion to the injection piston to give us the injection. So we've got this disconnect between where we could measure from and what the piston is actually doing. And when we actually compare the outcomes of those two measurements, we do see this slight deviation here, which is of the order of 300 microns, which doesn't sound like a lot from a machine perspective, but when you equate that to an actual volume of material, it can be the entire molded part in error between what your machine is telling you and what we're actually measuring off the system. Now we can correct for it. It's not a big issue. We've just got a kind of Hookean sort of spring response of the belt on the machine there, and basically with increased pressures, we see this differential increases because we've got this kind of elastic behavior in the system. But this kind of measurement allows us to implement those changes. We can modify our results so we understand exactly where the flow was at a given point in time. We actually collect all this information over Ethernet. So we've got a National Instruments box in the side of this machine, which takes this data alongside injection pressure data, thermal data, and a range of other things. So we can capture that on a per cycle basis, or we can monitor a run over a length of time as well. So these are the kind of data sets that we get. Once again, one of the advantages of having a separate data acquisition system is it allows us to make measurements much more quickly. So we're sampling much faster than the machine could sample in this case. So we can see these very, very fast responses. I mean, you can see here, everything is happening in a fraction of a second for the micro-injection molded part. So this is the filling profile here. So basically that's happening in just a few milliseconds. This is for a reasonably large component. But we can generate all this kind of data, and we can start to see when things are occurring. So we've got injection pressure, we've got infrared temperatures, all these things we can use to be able to quantify what's happening in the cavity. And it's also very useful for benchmarking simulation software as well. So that's all well and good. We've got these individual point measurements inside the cavity, so we can start to get an understanding of what's happening with the environment. But we've also spent time developing is actual visualizing what's happening in the mold tool. Why just have one measurement when you've effectively got a sensor array and a camera that you can use to actually image directly what's going on in the cavity? So we spent some time over the last 10 years developing our imaging capability for these kinds of processes. Now the problem is, these things can fill in less than a millisecond in some cases, so we need very, very high speed acquisition in order to get the data out for these kinds of processes. So we're generally dealing with very high speed camera technologies. This is the camera we have in the labs at the moment, which basically will record at about 5,000 frames a second at full HD resolution, but we can actually reduce the window size as well, so we can take fewer pixels and we get a linear increase in the rates. So we can actually sample all the way up to 1,000,000 frames a second if we want to. We're dealing with less than a microsecond exposure times, so we get really nice sort of crisp images. We do need a fair bit of light in order to achieve those. But it can also write an awful lot of data, so it's about 64 gigabytes of data in 2 seconds. So data management becomes a bit of an issue with this. But once we have this, it gives us a unique capability for looking at processes and understanding them in a different light. So a nice example here is I discussed weld lines before. Weld lines are a problem in conventional injection molding. They're a huge problem in micro-injection moulding. Because everything's cooling so much quicker, you have even greater weaknesses with a weld line in a micromoulded part because they don't have time to knit together. Everything's happening too quickly and it's cooling much more rapidly. So we actually used a system here to measure the kind of velocity that these flow fronts come together, and from that we can calculate the influence on weld line strength.